Okay, so let me say a couple words against someone. I have a problem. So I'm gonna show off my age here. What sizes of boxes of nuggets come in now? Let's see how many homes enthusiasts we have. Yeah, the big 20, right? It used to be, back in the day, the McNuggets came in three kinds of boxes, 6, 9, and 20, right? And that's the only size you can get. I guess not counting the kids meal, but you get a box of 6, 9, 20. So you could have 16 nuggets if you wanted, but you can't have 5, right? You also can't have 7. Agreed? What is the largest number of McNuggets that you cannot get by ordering packets of 6, 9, and 20? This is actually a famous math problem that actually has a lot of application, just in addition to my bad diet. And it turns out that 43 is the largest number of nuggets that you cannot order using boxes of 6, 9, and 20. Right? However, 44, 45, on up, you can get them all by ordering 6, 9, and 20. Prove this by induction. So there's two things to do. Number one, show that you can't get 43 out of 6, 9, and 20 boxes. And then you have to show that for every n greater than or equal to 44, you can get McNuggets, that many McNuggets ordering those many boxes. Here's a couple of induction problems. And number 2, these ones, I think, in my humble opinion, you can't just write down and go. I had to do some scratching on some other pieces of paper. I needed to do some mathematical scribblings with the result to figure out what I needed to make the ladder work, right? You're probably going to have to do that here. Show for all integers n greater than or equal to 2, the square root of n is less than 1 plus 1 over radical 2 plus 1 over radical 3, yada, yada, up to plus 1 over radical n. And this is true for n greater than or equal to 2. Show for n greater than or equal to 6, n to the nth power is strictly greater than 2 to the n times n factorial. Couple of things. If necessary, you're free to use the binomial theorem, which you can find in the notes, which I'll probably get to before Friday, but you can look ahead for it. The binomial theorem, I don't know if you've heard that name, but you all have seen that. It would have appeared in a pre-calc class or an algebra class or something. You're free to use that to help you out here. And you're free to use a calculator to check the base case for this, right? Because the base case will involve the 6. And that's number 3, how many of you have heard of the Fibonacci numbers? Right, this shows up all over the place. It shows up in art, it shows up in nature, patterns of honeycombs, sunflowers, all kinds of things. It's defined recursively by the first 2 numbers in the Fibonacci sequence are 1. And then after that, every new number in the sequence is the sum of the previous 2. So this means the next number is the sum of the previous 2 for all n bigger than 3. So it goes 1, 1, and then 2, and then 3, and then 5, and then 8, and so forth and so on. Show the GCD, the greatest common divisor of any 2 Fibonacci numbers in a row is 1. Show that the GCD of every other is also 1, right? Induction would be helpful. And finally, this is kind of cool. Let alpha be 1 plus square root of 5 over 2. Anybody know what this number is? This is kind of a special number. Has anybody ever heard of golden ratio? That's right. Yeah, that's what this is. Show that, and again, this one shows up in art quite a bit. Da Vinci was interested in this. Show that this crazy number here, alpha, which I'm a lazy man, I will write instead of 1 plus 5 over 2 because it's easier. Show that this number to the n minus 1 is greater than or equal to the nth Fibonacci number for all n and n. And I'll give you a hint. Alpha is a root of this polynomial, and that might actually help you in your quest to do induction. And finally, I think 4 is one of the easier problems, actually. Show that for all n and n, we have that the sum from k from n plus 1 to 2n 1 over k is the sum from 1 to 2n, a -1 to the n plus 1 over m. So these other ones, the stuff in red, you don't have to turn in, but you can, here's some, I've got a bounty on these for extra credit. The time limit on these are in the course, right? At any point you can turn these in. Find a formula, for the integral from 0 to pi over 2 of sine of 2n plus 1 x dx, for n 0 or natural number union 0, and verify that this formula works. I'm gonna do one very similar to this, actually, so it might be. Show by inductions or any means necessary, you can Malcolm-X this thing if you want, that k equals 0 to n minus 1, minus 1 of k, n minus k to the n is n factorial. And show by induction, this crazy business holds as well. So we've got a bounty on those extra credit, anytime before the end. Okay, any questions? All right. Let's do some more induction. Okay, are there any questions over what we did last time? So I'm gonna fill in some examples. Remember how to spell this name? Maltz theorem. How many of you have seen this before? That cosine theta plus I sine theta. And here I is what I think you might think it is. It's square root of -1. The n time. If you had a really smoking good trigonometry class, you might have seen this, right? Okay, let's prove this by induction. Here, we make clear in natural numbers and we'll say I have the square root of -1. Okay, I'm digging the base case. Number, cosine theta plus I sine theta to the 1 power is same thing as cosine 1 theta plus I sine 1. Base case, easy peasy lemon squeezy, right? No problem there. Now we have to jump to our inductive hypothesis. This is where we build stairway to heaven. We gotta build a ladder. Suppose for some m in the natural numbers, we have cosine theta plus I sine theta to the m is equal to cosine m theta plus I sine. This is our inductive hypothesis. This is the nth step of the ladder. We got to go to the n plus 1 step of the ladder. Well, let's see what happens. Any ideas on what we might do here? Okay, right. Let's use what we got here. Let's bootstrap it. The n plus 1 power is just this thing and one more power. Right? So let me break this down this way. Agree? Now, let's use our inductive hypothesis. Let's use my nth step ladder, right? How can I rewrite this? So I can rewrite this as by the inductive hypothesis. I can rewrite this bit as cosine m theta plus I sine m theta. And then I multiply this by cosine theta, sine. Everybody? Yes.
Like when you write it, like when you do the inductive hypothesis, how is that not just like setting the, like how is that not just going from what you're trying to prove and then just.
She's asking, correct me if I'm wrong, she's asking, aren't you assuming the conclusion, right? That's a good question, but that's not what I'm doing here. So everybody understood the base case, right? The bottom rung of the ladder, right? Just where I plugged in one, right? That works. I'm not assuming this. What I'm doing is I'm saying, if this is true, then the next step is true. I'm not proving this. I'm proving the m+1 case, given that the m case works. That's the way induction works. You've got the bottom rung on your ladder. That was the base case one. That's step one. What we're proving now is if you have any rung on the ladder, say the nth step, then we're going to get the m+1 step, and this builds the ladder. Because now that you've got the first step, if you have the nth step, you have the m+1. Well, you got the first, so you got the second. Well, now you got the second, and if you got the second, you got the third, and that's how the ladder works. Is that clear enough?
Yes.
Okay, everybody agree this is going to be a complex number, right? It's going to have an I part. So I'm going to break this down, and I'm going to get, so I'm going to multiply this way. I'm going to get the real part. So this is going to be cosine m theta, cosine theta, plus, when I multiply these two, it's going to be real, right? Because I times I is -1, right? So I guess that's actually going to be minus sine m theta, sine theta. Everybody agree with that? And now I'm going to try to surgically remove the I part. And I'm going to get my I part by doing this and this. So it looks like cosine m theta sine theta plus sine m theta. Cosine. Everybody agree that that's what I get when I multiply out this mess? Look at the mess I made. Anybody, any idea how to move forward?
Those are the trigonometric.
Righteous. Good shot. All right, so let me remind you. And sine of A plus B. Or remember right, sine A cosine B plus cosine A. Right? So this is actually, isn't it? Let's kind of write it down and check that this is right. Because this should be cosine cosine. There we go. Minus sine sine. So that works. Let's see, let's check this. This should be sine cosine. There it is. Plus cosine sine. There it is. And this is cosine m+1 theta plus I sine m+1. So formula works. Questions on this? Any questions? Yes,
So been following all this, just wrap up.
I'm sorry.
You've been following like, just wrap up with the, we need to explain.
You know, if you're talking about writing up homework, I'd take the extra time to be careful with the language. The answer to your questions, I don't know. It depends on how clear you are, and that's a judgment call. I get that. Whether I read it, whether the TA reads it might be different. Just for all the points, just be careful on this. By the way, let's say something about the exam. I know that when you all take the exam, you're in a little bit more of a hurry. And the parts that I asked you to actually prove, they won't be as hard as the ones on homework, obviously, but I tend to give a little bit more latitude. You know, when you've got that kind of time limit. Okay, let me ask you a question here. I hesitate to write this up here because what I'm gonna write is an obvious lie. And I don't want this to go up on YouTube because I'll be appointed to the cabinet tomorrow. But let me give you the following example. This is why we need basic cases. I claim all integers are both even and odd. I'll agree that this is a ridiculous claim, right? But proved without put quotes because it's not one, but proof. If n is an odd, then n plus one is even. Can we all agree with that? That if I had an odd integer and I had one to it, it's even. Agree? And if n is even, then n plus one is odd. Everybody agree with that? Now let's suppose the natural number and n is both even and odd. Now let's build the ladder. If m, well, let me say, since m plus one is odd, and since m is odd, boy, you walked in at the wrong time. Please, this is a lie, by the way. Look at here. Since m is odd, m plus one is even. So m plus one is also both even and odd. And if m is even and odd, so is minus m. So this whole problem. There's a couple things wrong with this proof. There better be, right? There better be. But the induction is solid, right? This part of the proof is true. Suppose m is both even and odd. If it's even, then m plus one is odd. And since it's odd, m plus one is even. So if you ever have an integer is both even and odd. When you add one to it, it's both even and odd. So inductively, everything's both even and odd. What's wrong with this?
Since your starting assumption is wrong, any conclusions you make based on that will also be wrong.
But I didn't, really make an assumption, right? Do you agree with this, that if n is odd, when you add one, you get an even, when n is even, you add one, you get an odd? And then I said, if, this is both even and odd, and the next one is, right? I mean, you're sort of right about.
Right,
yeah.
but like to start about.
Well,
like,
what's wrong,
that's the-
what's wrong with it? I mean, this is an inductive proof, right? What's wrong with it? Yeah. There is no bottom rung to this ladder, right? If there was any integer for which this is true, it would be true for all the next ones, but there aren't any, right? This is the importance. So I call this example, yes, we do need a base case, right? Because I did build the stairway to heaven, but there's no starting point at all, right? There's no place to get in the door because there is no integer in the first place that is both even and odd. You can prove that. This is actually, as he points out, this is another good example of, if you start with a false premise, you can get all kinds of crazy stuff. But the induction, this step is solid. The problem is there's no integer that is both even and odd in the first place, right? And so that's the importance of the base case. Let me give you another example, and this might be useful. Here's a couple of examples where multiple base cases might be needed. Feel obligated to write this. There's no base case to start off with. Here's an example. I'm going to find the Fibonacci numbers this way. I'm going to find F1 equals F2 1 and Fn equals Fn minus 1 plus Fn minus 2. We're all greater than 3. As I pointed out, these are kind of important numbers. The first two are 1. And they progress by adding up like this. Here's what I want to prove. Fn is less than 2. Prove that every Fibonacci number is bounded above by 2 to the n minus 1. I am actually going to do 2 base cases, but then I want to identify well, actually, let me start this proof sort of incomplete. So I'm going to come back to this. Let's assume that we start. It's very natural, I think, to start this off. The base case n equals 1, like because n is in the natural numbers. It's very natural. Like, okay, let's do the base case. For n equals 1, we have F1 is 1, because that's what we said it is. And 2 to the n minus 1 is 2 to the 0, which is 1. So F1 plus n or equals 2 to the n minus 1. There's my base case, right? Now let's suppose that I went on very happily and said, okay. So for n greater than or equal to 1, we have Fn is less than or equal to n minus one. And we need to show f n plus one is less than or equal to n. Everybody agree with that? This is the ladder, right? I need to show that if this works, then the next step works. Everybody okay with that? Okay, so, yes,
Okay, have one is your base case and then. If minus
Spidey sense is tingling, right? You put your hands right on what we're gonna run into in just a moment, right? Exactly right, gotta be careful. Let's go through this naturally, right? I wanna do this, right? And somehow I wanna show this is less than or equal to the n. So what do you suppose I'd say about f n plus one might help me out? In the Fibonacci sequence, every term is equal to the sum of the two previous terms, right? So what are the two previous terms here? Fn and what? And this is exactly the problem. What's the problem with this? That's right. If you're at the case n equals one, you're hosed here because there is no zero. So let me fix this in orange, right? I needed another base case. This wasn't good enough. I don't have enough steps on the ladder to go up. Like just one ladder by itself is all eaten by termites and rot. Let's do another base case. Well, let's check this for n equals two. For n equals two, I have f2 is equal to, again, one, right by my people. And two, and the n minus one in this case is 2 to the 1, which is 2. So Fn is less than or equal to n minus 1 for n equals 2. I needed two steps on that ladder. And so now I can go to the top of my ladder case, right? Because I've already got one covered. I have Fn is less than or equal to the n minus 1. Need to show Fn plus 1. This is all still good, right? Notice I'm good now. Everybody agree with that? Why am I good? Because n is at least 2. So this is at least 3. And this is F3 is F2 plus F1. These are all legitimate things. And I've covered them in the ladder, right? I've covered the F2 case and the F1 case. Everybody okay with that? So let's go on from here. What can I replace Fn by? 2 to the n minus 1, agree? And what can I replace this by? 2 to the n minus 2. Everybody agree with that? Anybody see anything I can do with this? And this is equal to 3 times 2 to the n minus 2, which is less than or equal to 4 times 2 to the n minus 2. And what's special about 4? So in particular, Fn plus 1 is less than or equal to n. And we've built the ladder. Does everybody see why we needed two base cases here? Because otherwise I'll run into problems. Sometimes these are not so easy to spot at the outset, and this is why I say with a lot of these inductive proofs, what happens is there's nothing wrong with you getting a few steps into a proof and realize, oh crap, I've got a base case, right? That's fine. That's why you do it on scratch paper first, go back and polish it. Yes. NTS, what is that? Need to show, right? I'll use that abbreviation. So this, by the way, yeah, so I just write that down. let you guys know where we're headed. Here's a note. This is kind of, I like this one. It's similar to, nuggets, although a little bit simpler. Um. Show. Amount. Of postage. Over 5 cents. And you covered. With 3 and 4 cents. So. Everybody knows what stamp is, right? I don't think people use letters anymore, but so suppose you want to send a letter, and all you've got is 3 and 4 cent stamps. Is it clear that you can't cover postage of 5 cents with this? But you can cover 6, can't you? And you can cover 7. And I guess you can cover 8 too, can't you? And now I'm starting to see a pattern, you cover 9, but how do we know, this? So another way to formulate this is show any, natural number n greater than or equal to 6, is a, can be written as X is how many 3 cent stamps, Y is how many 4 cent stamps, right? Anybody agree with that? By the way, what are my restrictions on X and Y?
Actual number.
More, right, or 0, right? Because you might use 0 stamps for, like, for example, 16. More 3 base cases. How do I know that? Because I've already done the problem, right? This is not the doing prestidigitation. I know how this works. But there's another way that you can see it after you've done the problem. Well, let's write a solution for this. 3 times 2 plus 4 times 0 plus 6. So that works. Right? N equals 7. 3 times 1 plus 4 times 1 equals 7. So that. And what else? I need 8. 3 times 0 is 4 times 2 is equal to 8. So that works. By the way, you're always safer to do more base cases than you need, but please don't do a million. You should probably figure out what's a pretty good economical to do. You'll see why we need 3 base cases in just a moment. And the problem itself will shed light on why there had to be 3. Inductive hypothesis. Let's suppose, and actually I'm doing something here. Let me write it over here. I'm going to do something that I'm going to set on firmer ground when we get done doing the examples. Let me write down. how does an inductive hypothesis usually work? You usually show that if you have the nth step on the ladder, then you can get n plus one, right? So you use the n to get the n plus one. There's a stronger form of induction where you don't necessarily have to use the nth step to get the n plus one. You can use the nth step and any of the previous steps. So in other words, what we're doing, what I did with induction most of the times, I assumed I had the nth step and I've got the next one, right? I'm gonna assume something stronger. Not only do I have the nth step, but I have all the runs in the ladder up to that. Right? So instead of just considering M in a vacuum, I consider M in any of the previous runs. This is called strong induction, and it's equivalent to induction, and I'm gonna prove that later, but I will use that freely now. Yes.
Can you set the X for any of those three X's for one, you just set it equal? Response to the negative. What did you choose to in this case?
What, right here?
No, it's not right. You,
This?
yeah, you used 0 and you used 2, why didn't you use 1?
No, no, the two is what's multiplying the three. I've got 3 and 4 cents stand.
Oh,
The smallest number I can make is 3. Okay, other questions? So here's my inductive hypothesis. Uh, Mark A. Uh, uh, okay, assume m is greater than or equal to 8. This was the last base case that I have. And I'm assuming something a little bit, of course, m could be much bigger than 8 if you like, but I'm assuming something stronger here. I'm assuming that for all runs on the ladder between 6, my smallest base case, and wherever m is, which is at least 8, that this has a solution for some x, y, and n0, right? So basically what this says is not just m works, but every L between 6 and m. So m works, so does m minus 1, m minus 2, all the way down to 6, right? So this is a little bit stronger. I'm just saying my run that I'm on is not in a vacuum. All the previous runs are there. Now I've got to show that the m plus 1 is there. Right? So here's our inductive hypothesis. Now consider m plus 1. And of course, I need to write it in this form. Right? M plus 1 is greater than or equal to what? Everybody agree it's greater than or equal to 9? Now, what's the smallest value of stamp that I have? I've got a 3-cent stamp, right? So everybody agree? So by inductive hypothesis, this m minus 2, that's at least 6, right? Is that one of the rungs on the ladder? Yes, it lands, it's greater than or equal to 6, so it's one of the runs on the ladder. So what do I know about n minus 2? I can do the postage, right? 3x for y, or some x, y. Everybody agree with that? I can do the postage. But I don't want the postage for that. I want the postage for n plus 1. Stick on a 3-cent stamp, right? Because I've got n minus 2, there's the postage. I need x 3 cents and y 4 cents. Stick on another 3. So we're done by induction. Everybody agree with that? I built the, yes.
I can't.
What's that now?
I can't reason.
Right, but that's not what I claim in the problem. So I think your point is, yes, you can make postage for 3 cents. Yes, you can make postage for 4 cents. We can all agree with that. But we're ignoring that because you're asking a broader question than I asked, right? You might ask the question, for what postage can you make, right? And the answers to that would be 0, if they let you do that. 3 cents, 4 cents, and then 6 cents and above. Okay, yes.
Can you show like why we would like the basis of like n equals 7? Like, or like why do we need more than just like, why do we need 6, 7?
Because what we did here is, so we've got all this, we need to find postage for n plus 1, which is at least 9, right? And the way that I chose to do that is I'd like to be able to find postage for 3 cents less and then stick a 3-cent stamp on it, right? So that was my attack. But for me to be able to subtract 3 points off the ladder, right, I need to know that the previous 2 rungs were. Is that cleared up?
Thank you.
Okay, now, I'm not completely freaking out. Any questions? I've used induction to prove things so far. But inductive ideas are actually important in physics, they're important in mathematics, they're important in every discipline of science. Sure, we're building up things. I'm not gonna be able to finish this today, but I'm gonna start it. I want to find out cosine 2nx. I want to find the integral of from 0 to power 2 of cosine 2nx. So I want a formula that gives me like cosine 0x. If I can do that, this is integrating 1. Cosine squared x, cosine 4. I want a formula that tells me what the integral of that is, 0 to power 2. This is actually very important if you want to figure out what the volume of an n-dimensional sphere is. And I don't just mean 1, 2, and 3, I mean any dimensional sphere. This is an important piece of finding volume. So how do we do this? Well, this is unlike the other problems that we've done because I don't even have the answer yet. I mean, usually I say, oh, here's something that's true, proved by induction. I don't even know what the answer is yet. But I'm going to use the inductive ideas and see if I can figure it out. What's the first n for this to be relevant? It's 0. Right? So I'm going to call this, so I don't have to write this anymore. I'm going to call this I2n, right? Signifying that. I zero, I think. It's just one dx, right? Antiderivative is x from 0 to the power 2 to the power. Everybody okay with it? Now, it gets kind of crappy after 0. I mean, 0 was kind of easy. What gets bad about this? What's the annoyance of integrating cosine of 2x? Or I'm sorry, cosine squared of x.
Cosine squared of x is
Well, so the problem is you have to use this crazy trig stuff, right? I mean, if you remember back to when you did Calc 2, you'd write cosine squared x is 1/2 plus 1/2 cosine of 2x, and boy, it gets worse after that, right? So what I'm gonna try to do is I'm gonna try in general to do the following. I'm gonna try to do integration by parts and bring this down. So let's look at I2n plus 2. That's this thing. Anybody agree with that? So let me write this out this way. Any suggestions on what I might do here? Any ideas? How we're gonna integrate cosine 2nx times cosine squared of x.
trig. Cosine squared, sine squared.
Okay. So the suggestion is, I think this is 1 minus sine squared x. Yeah. Okay. So if we did that, if we went down that trail, this would become do that right? I agree. But now what? Well, let me write this way. We've sort of got two problems here, don't we? Point out this one is actually. Right. So what we've got so far is this. And I think I'll leave you all to think about this and we'll finish up this problem next time. But let me kind of collect what we've got so far. Where did we start? And what do we have? Everybody agree with that assessment? The problem is, how do you do this? So let's think about this for next time. Let me give you a hint. Write this as sine x, like sine x, and see if you can use integration by parts. We'll finish this up next time. By the way, there's, and especially when it's called, there's a smoking good math book today. It's actually on the fundamental theorem of calculus, and there'll be some proofs. The guy that's giving the talk there, he's really good about this kind of thing. So if you got some time, I'd encourage you to be there. Otherwise, have a good weekend, and we'll see you on Monday.